Welcome back to Math 109 Plane Trigonometry. In this video we're going to take a look at DeMoivre's theorem, which is useful for finding powers of complex numbers. So in the in-class activity on Wednesday, we, in the last few problems, took a look at taking powers of just a generic complex number, RCIS theta. And from that activity we kind of implied that RCIS theta to the nth power is equal to r to the n CIS in theta. Now, at least we can see that this holds true for the positive integers. And it turns out that this holds true for any real number, but you're not going to have the ability to prove that until you get enough higher mathematics under your belt that you can look at complex analysis. But we do have the firepower to prove that this is true for the positive integers. The method we're going to use is known as proof by induction. So we want to start with a base case. We're going to let n equal 1. So if n is equal to 1, then r CIS theta to the first power is equal to r CIS theta, which is equal to r to the first CIS 1 theta. So that's all fine and dandy if n is equal to 1. So now what we're going to do is assume that our statement is true for n equals k minus 1. And then we want to prove that it's true for n is equal to k. So, we know that r CIS theta to the k, just by the definition of that exponent, is equal to r CIS theta to the k minus 1 times r CIS theta. Well, now we use that inductive hypothesis that we mentioned. We're assuming that our theorem is true for smaller values of n. So, we can assume that. So we'll go ahead and do that. So r CIS theta to the k minus 1 is equal to r to the k minus 1 times CIS of k minus 1 theta. I'll put some more parentheses in there to make that more clear. And we'll multiply that by r CIS theta. Well, now we can apply the product theorem from last time. And we know that this is equal to r to the k minus 1 times r times CIS of k minus 1 theta plus theta. And now simplifying that, r to the k minus 1 times r is just r to the k. And k minus 1 times theta plus theta is going to be k theta. So we get r to the k, CIS k theta, as the theorem says we should, and that is deemed sufficient to prove the theorem for the positive integers. Now, like I said, this is true for any real number value of n, but we don't have firepower at this point to prove this for anything other than the positive integers. However, we will in the next video be using this to take roots of complex numbers. So that's it for this video. In the next video, we are going to take a look at taking roots of complex numbers.